And so what I'll do is I'll explain like where it comes from or what it's based on, and then show you where you would apply it. But for both the law of sines and law of cosines, these deal with triangles that are not right triangles. And so anything that's a right triangle, and it's kind of like some of the other things that I've talked about. Because we're talking about it right now, many of you will want to apply this to everything. It does work with right triangles, but it's less efficient. I mean, it's more efficient to use the trig ratios for right triangles. And so this is only for use in non-right triangles. And those will be referred to as oblique triangles. And so oblique just means non-right. You'll see it when we get to solids as well. And it would also describe angles that are not right angles. So acute and obtuse angles are also considered oblique. All right, as far as taking a triangle that is not a right triangle. Guys, quiet please. Okay. If you were to label this triangle ABC with sides A, C, and B opposite each of those, okay, what you could do to derive the law of sines is if you drew in an altitude, the altitude breaks this triangle, this non-right triangle, this oblique triangle, into two right triangles. Okay, I'm going to call this H, the height or altitude. And for each of these triangles, you can now set up a trig ratio, right? You have angles A, you have the opposite, and you have the hypotenuse. Well, opposite and hypotenuse relates to which trig ratio? Sine. So what you could say is the sine of A is equal to the ratio of opposite over hypotenuse for that particular triangle. You could do the same thing from C right here. You could say you have an angle, the side opposite, and the hypotenuse. So again, which trig ratio is that? Sine. So the sine of C is equal to opposite H over hypotenuse A. Okay. And so how you can derive this law of sines is if you solve for the common variable in each of these equations, which is what? H. You would do that by multiplying both sides by C here, both sides by A here. Those would cancel, these would cancel. So you get H is equal to C times sine of A. Well, H is also equal to A times the sine of C. And all the law of sines does is it puts the variables with the same letter, even though they refer to angles in opposite sides, but they put them on the same side. So if we move the A over, and at the same time move the C over, you get the law of sines, which states in an oblique or any triangle, the sine of an angle divided by the side opposite that angle is going to have the same ratio for all corresponding angles in opposite sides. So the sine of C is equal to small c. Well, the whole same thing holds true if we had done it for B as well. So the sine of B over the side opposite it. These are all going to have the same ratios. And the law of sines can also be flipped the other direction, meaning you could also say that the side of an angle divided by the sine of the angle opposite it has the same ratios for all corresponding angles in opposite sides. So is equal to B over sine of B is equal to C over sine of C. Okay. Will, question? H? H is the height. When I say H here, or H here? Here it refers to the height of the triangle, or altitude. It's not a hypotenuse, it's a leg. Okay, so these two forms are the law of sines. And the law of sines can be used in any triangle. But again, if you have a right triangle, you might as well use the trig ratios. They're a lot more efficient. And the law of sines is just going to lead you to that anyway. It's going to take you right to the trig ratio, but it adds an extra step or two. Okay, there's three patterns that this works for. Okay, this works for any pattern where you're given two angles of a triangle. So ASA and AAS. Those are the main patterns that you're going to use law of sines for. Okay, and then it also happens to work with SSA Is SSA a congruence pattern? Is it one of the 4 congruence patterns for triangles? No. And so what you're going to see when we go through SSA here is oftentimes there may be 2 possible triangles if you're given SSA, which is, again, why it's not a congruence pattern, because there may be more than one triangle that you can take away from that. Okay, so let's look at each of these cases and see how the law of sines could be used. And let's look at ASA first. Okay, so assuming this is not a right angle here, and let's say we were given in triangle ABC, we were given 2 angles and the included side. And so if we wanted to find, let's say this is 50, say 60, and let's say the side in between them is 10, just to use kind of easy numbers here. Right, if we are going to use law of sines, what we're going to be able to find is anytime you use these, again, you're only going to use 2 pair of these. You're only going to compare 2 ratios. You're not going to do all 3. But in order to do this, what you see is you have to have 2 known angles and 1 known side, or vice versa. 2 known sides and 1 known angle. So here you have 2 angles and a side. And do you know what the sides are opposite the 2 given angles? No. So can you use those 2 given angles? Not right away. Okay. In order to set up your ratio, you need to know the angle C. Well, can you find angle C? Yeah, using triangle sum. What is angle C going to equal? And so if you find that, you can now identify what your ratio is. Your ratio is the sine of 70 over 10. And that ratio is going to be consistent with all opposite sides and opposite angles. So let's say we're looking for side A. And the reason why I put these in 2 different forms is I would strongly encourage you to start with your unknown on the top of your fraction. And it's simply because it gives you less steps. It gives you 1 fewer step than if you put it on the bottom. So if our unknown is A, we can set up the ratio of A over the sine of the angle opposite it, which is 50 degrees, is equal to the known pair. So the known pair is a side of 10 over the sine of the angle opposite it, which is 70. And so now, in order to solve for A, rather than cross multiply and then divide, we set it up so that all we need to do is multiply both sides by this denominator, sine of 50. And that will give you your solution. So A is equal to, and now you just multiply this through. So 10 times the sine of 50 divided by the sine of 70. And you get your A value to be approximately 8.15. And now, is that something that you would expect? So here we have an angle of 50, an angle of 70, an angle of 60. And the side opposite the angle of 70 is 10, so what would you expect about the side opposite angle 50? Is it going to be larger or smaller than 10? Is that consistent? Yeah. Let's see if we can find B and see if that fits the same, again, consistency. Okay, we take our unknown side over the sine of the angle opposite it, so sine of 60. Set it equal to the known ratio. Now, you could use either one. You could go 8.15 over 50, sine of 50, or 10 over sine of 70. Which one's more exact? Right. This one is exact, where this is an approximation. So use the exact one anytime you can. So 10 over sine of 70. And then we can solve this by doing the same process, real simple. Multiply both sides by the sine of 60. And we get our value for B, which again, when you calculate this through, 10 times the sine of 60, all divided by the sine of 70. And that equals about 9.22 if I round it to 2 decimals. Okay, so this is going to be about 9.22. Is that consistent with what we would expect based on the angles of the triangle? Yeah, it's smaller than the side opposite 70, but larger than the side opposite 50. So it's consistent with everything that you can check or estimate on. And so that's what you would use to find the measures for any side of a triangle if you're given two angles and the side in between. Let's say you're given two angles and the side opposite one of those angles. Okay, so again, if we label these just to have a nice easy reference for the sides that we're looking for. And so here's the pattern of AAS. Again, it's not saying that you're using congruence patterns, it's just giving you a pattern of information. Two angles and a side that's not included between them. Okay, which side can you find easiest? You have your set ratio, sine of 40 over 10. What you don't have is side opposite A, you don't have the side opposite C, and you don't have the angle C. So can we find angle A, or the side A? Yeah. Set up your law of sines ratio. A over the sine of 80 is equal to 10 over the sine of 40. Multiply both sides by the sine of 80 to solve your equation. And again, as you go through this, sine of 80 times 10 divided by sine of 40, you get A to be approximately 15.32, okay, which is consistent. It's greater than 80 degrees. Okay, what is angle C going to be? Okay, so this is going to be 60 degrees. So when we set up to solve for side C, we get C over sine of 60 is equal to 10 over sine of 40. So again, we can calculate. And we get our answer to be 10 times the sine of 60 divided by the sine of 40, about 13.47. Is this all consistent with what we would expect? It's greater, it's the middle length side opposite the middle measure angle, the smallest side opposite the smallest angle, largest side opposite the largest angle. Okay, so it fits with that. Okay, are there questions on this?
When you say sine 80 times 10,
All right, so if you're taking this calculation, you can take 10 times, go to your sine key, sine of 80, and then divide by sine of 40. I'm putting a decimal in there just so that my answer comes out as a decimal. And that's all you have to do. It'll do order of operations there for you, and so that would verify 15.32.